I'm back at CERN. We've been here several times before, trying to understand how the universe works, what the scientists here call the standard model. But this time, we're here to look beyond the standard model.
The Standard Model is a theory that describes all of our understanding of the fundamental particles that make up nature and the forces that interact between these particles. So in fact, in the Standard Model, it encompasses all of the forces and the particles, but it doesn't include gravity. And we know gravity exists, so this is in fact one of the main reasons to look for a theory beyond the Standard Model where we can mathematically include gravity inside the description of the theory. But the reason that gravity doesn't matter at experiments that we do at the LHC is that it's very, very weak compared to the other forces. So the effect of gravity in the physics that we look for in the LHC is basically not relevant, and therefore we can study the other forces with the LHC collisions.
So the standard model kind of describes the physics we can see. I mean see in the sense of see and detect.
Yeah.
But you're looking for the kind of physics we can't see.
Yeah, so I think there's two kind of areas why we think we wouldn't have seen yet the physics beyond the Standard Model. So one could be that the new particles that make up this physics are too heavy. So they're too heavy to be produced in the collisions in experiments.
Oh, because we just simply don't have the energy to do it.
Exactly, and that's why the LHC was a really important machine, because it had 10 times more energy than the previous collider. And so this means you can produce particles that are 10 times heavier. And so this allowed us to discover the Higgs boson, which is quite heavy. But there are theories which have particles which are sort of 10 times heavier than the Higgs boson, and this is what we're kind of looking for in the LHC collisions. So that's one aspect of how we could look for new physics beyond the Standard Model. Another thing which has become more popular recently is thinking the new particles could in fact not be that heavy, they could be light, but they could be very weakly interacting. So that means that they just don't talk with very much interaction strength to the other particles. And that means you have to have a huge number of collisions to be able to see these new particles. And so at the LHC, we're kind of looking for both of these things. So light new particles which are weakly interacting, or heavy new particles where we're really using the energy of the LHC beam to produce the mass of these heavy particles.
We're here to see one of the experiments that's looking for those particles. CMS, which stands for Compact Muon Solenoid, is one of 4 major experimental detectors placed along the Large Hadron Collider. It smashes particles together at 1 billion kilometers per hour, or nearly the speed of light. And remember, nothing in the universe can go faster than the speed of light. I'm with Claire Lee, a particle physicist at the CMS experiment. Nice to meet you, Claire.
Nice to meet you.
Thank you for having us. And we haven't got much time, so we're on the run, right?
Yeah, let's go straight down
Let's
underground. Go. Cool. This is the elevator over here.
We're going to go down.
We're going down. down, in and around. All right, so I need to go through these green doors here. It's an access requirement. I need to scan my dosimeter.
A radiation dosimeter.
Yeah, this is my personal dosimeter. It monitors my cumulative radiation dose throughout the year, although right now there is no radiation in the cabin.
Because it's not working now.
It's not working right now, which is why we can go underground.
Yeah. Claire's got to get a retinal scan because only authorised people are allowed down there into the detector itself. And now, it's time for us.
All right, helmet for you, just in case our...
Oh, it fits. That's very unusual. That's marvelous. Thank you.
Just in case our 14,000 ton detector falls over onto your head. It's
quite right. Where to next?
To the elevator.
Oh my God.
Do you want to press the button?
Oh, I do want to press the button. Because this is our 4th detector at CERN, and it's the first time we've ever been able to get down into the detector.
Really? That's more exciting. So you are definitely coming to the best detector of them all.
I knew you'd say that.
Of course. Might be a little bit obligated. But I have seen all 4 of them, so I do think I have experience.
Mostly we've had to film outside with the big murals because they've always been active, but at the moment this one's not working.
Right, well actually the whole LHC is not working. It's shut down for the winter period, for maintenance, some upgrades and stuff. But that means that we can go into the experimental cavern itself. And there are a lot of people working on the detector right now. So even the detector, some of the slices are moved apart.
Oh really? So it's pulled apart?
Yeah.
So that's ideal for us.
Absolutely.
The CMS detector is a beast of a machine. It's 15 metres in diameter and weighs around the same as 30 jumbo jets. And once again, because it emits dangerous radiation when it's working, it has to be placed deep underground.
I can show you how far we came down here.
Cool.
So take a look up there. That is the surface that we came from.
Oh my goodness!
This is the bottom of the small shaft.
So that's where we are now, 87 metres below ground?
Yeah.
So what are the little lights flying up there?
That's just some LEDs to show the data coming out of our detector
right.
and going up to the surface, ready to be analyzed.
Symbolic data.
Exactly, yeah.
And where are we now?
So right now, we are actually level with the LHC beam pipe. So at 4 points around the LHC, the two beam lines cross.
Yes.
And that's where the collisions happen. All right, and this is the final access zone through to the experimental cavern. Brace yourself.
I am. Great.
Because this is the most beautiful thing that you will ever see in your entire life. So welcome to the CMS experiment.
This is very, very exciting.
Go take a look over there.
Oh, wow! You weren't kidding.
Yep,
Engineers are really cool, aren't they?
they really are. She's beautiful, isn't she?
She's so beautiful. But it's called the Compact Muon Solenoid.
That's right.
It doesn't look very compact to me.
Actually, there is a lot of material inside this thing. There is 14,000 tons of detector in here. And when you think about 14,000 tons, that's actually pretty small.
What about solenoid?
So the solenoid is the magnet that we have.
Right.
We have the most powerful solenoid magnet in the world.
Right.
It runs at 3.8 Tesla when it's on. It's not on right now.
What's Tesla? A measure of magnetism.
Yes.
Right. So 3.8's a lot, I'm guessing.
3.8 is a lot.
Right.
And that silver ring over there, that is the solenoid magnet. So the point of the magnet is to bend particles as they come out of the collision.
Oh, I see.
Because if we bend particles, positively charged particles and negatively charged particles will get bent in different directions.
Right.
So we'll be able to tell the difference between them.
So we've already got compact, we've got solenoid. What's the M?
So the M stands for muon. Muon is like a heavy electron. So the same charge, but it's heavier, so it's got a lot more momentum. What that means is that muons that are created in the center of the detector and come flying outwards from the collisions, they go flying all the way out here.
Right.
And all of these panels that you see here in this slice and that slice over there,
Right.
they are specially designed to detect or catch these muons as they travel through them.
Muons are actually part of the standard model, along with particles like protons, neutrons, electrons and quarks. But all these particles only account for 5% of the universe. Everything else is a mystery.
So 95% of the universe is stuff we don't know.
So you're looking for the other 95% now?
Well, so the other 95% is split into two parts. There's a part that acts like energy and a part that acts like matter.
Right, dark matter.
Dark matter, exactly.
Right.
The energy type of one you need to look at with cosmological observations. So we need that to the astrophysicists too. Whereas dark matter, it's a thing, it's a particle. So the idea is that maybe we can create these dark matter particles inside our detector here at the LHC. And what can muons do? Well, one of the signals that a dark matter particle could leave is 2 muons flying through the detector.
How do we know that that's to do with dark matter? Let me see if I understand this. Theoretical physicists come up with an idea. I think if 2 dark matter particles collide, they'll create these muons. And then you build this enormous thing to check out that idea. Is that right?
Kind of. You know, it's a little bit weirder than that. So let's just take a step back, right?
Yeah.
When we started building this detector, the Higgs boson was not yet discovered. So the Higgs is part of the Standard Model. So you can imagine the Standard Model like a puzzle, right? With one missing puzzle piece. That was the Higgs boson. Now, if you have one missing piece in a puzzle, you've got the overall picture, you've got the shape of the puzzle piece, you know how it connects to the other pieces. So from that point of view, even though we didn't know the mass of the Higgs boson, we knew a bunch of other things about it. So it was relatively easy to go on a search for the Higgs boson. We just had to build something that could smash protons with a high enough energy. Now, the thing about dark matter is that Standard Model puzzle is only a small piece of the much bigger puzzle of the universe. But we don't know what the bigger picture looks like. We don't know what shape those pieces are. We don't know how they connect. So theorists have come up with many different possibilities of the way that these dark matter particles could connect to our Standard Model particles. And we have to meticulously go through each of these possibilities and searching for, to see whether or not this particular theory could be the right one that describes the universe that we have. Now, here's an interesting thing, right? The Higgs boson tells us that we have a Higgs field. And the Higgs field is what gives mass to all the particles. So the Higgs field gives mass to Standard Model particles. And because dark matter has mass, it's not a bad assumption that the Higgs field also gives mass to the dark matter particle. And that means that the Higgs could be a link between the two. So maybe we can smash protons together, create Higgs bosons inside our detector, and those Higgs bosons, instead of decaying to muons or electrons or photons or any of the other normal Standard Model stuff, maybe those Higgs bosons could, very, very small fraction of the time, decay into dark matter.
You're looking for something else, and it has a very cool name. It sort of sounds like Star Wars, the dark photon. What's that all about?
So remember our Standard Model puzzle, and then we want to extend it into dark matter. One possible way of extending it is to take our Standard Model and just make a copy of it.
Right.
That is now a dark matter version. So it has its own electromagnetic force and its own strong and weak nuclear force. So the photon is the carrier of the electromagnetic force.
Right.
So if we've made this copy, which we call the dark sector, then a dark photon would just be the photon in that version of the theory.
How will you know here that you've seen evidence of dark photons?
Well, one of the theories that predict dark photons say that these can decay or transform into muons. So you could have these muons coming out from the center of the detector. And in some cases, you could have a particle that lives a long, long time before it turns into dark photons.
Right.
So normally you see a muon track starting right at the center point and moving all the way outwards through the detector. But for example, if you had a new type of particle that lives a long time, that particle might get to here before turning into two photons.
Right.
So a very interesting analysis that has just been released is looking at these, we call them a displaced vertex. So the starting point is displaced from the center. So you basically are looking for two muons that are
arriving at different places on the detector.
exactly and
Right.
come from maybe a point out here rather than a point in there.
Photons, muons, Higgs bosons, all part of the trillions of particles that are produced at the LHC. After experiments like CMS generate billions of data points, it's time for theorists like Mark Riembosa-Peres to take over.
I've been to CERN 3 times now, but you are my first theoretical physicist. The LHC produces so much data, 40 million collisions a second. How do you keep up with so much data?
So you have to come up with assumptions that are broad enough that they can cover big parts of your data. So if there is something, let's say, unexpected, you could be sensitive to it. But also one has to keep in mind that we have a very rigid framework, a very rigid mathematical framework.
When you're saying framework, you mean the standard model, right?
Yeah, the framework is quantum mechanics and relativity, and we took all this data, and it seems that this standard model is the best way within this framework that we have to explain nature. But there are some gaps, there are things that we don't understand, and we try to modify this standard model, and we get what is called the BSM model, beyond the standard model. The standard model doesn't explain how galaxies rotate, so it's something very basic. The standard model also it doesn't explain why we're made of matter and not of antimatter. And this is also a very basic question. And in a sense, the standard model also doesn't explain why the universe is so large. And as a theorist, we don't like this. Every time we look at nature, we find explanations when things are small or when things are large. So it is natural to think that, what we know is not everything there is, so there are things that we still don't know. And beyond the standard model is the idea that there is an explanation to this.
If the standard model was the only correct theory, that would tell us the probability that something would happen when we collide these protons. So you would have a certain probability of creating a Higgs boson. The Higgs boson would have a certain probability of decaying into particles that we would then see in our detectors. But when we're talking about searching for beyond the standard model physics, again, it works in the same way that there's a certain probability. If you have a beyond the standard model theory that predicts that there's a new particle, in these collisions, these new particle could be produced with a certain probability. And what we do is we search for that new particle. We know how many collisions we've had. And this allows us to say, after we've taken a certain amount of data, if the theory was correct, we should have seen this new particle. And if we haven't seen it, then we can exclude that model, or at least the parameters associated with that model.
So you're like detectives looking for clues, and if you can't find the clues, you say the murder didn't happen.
It didn't happen in a certain way, exactly.
Right.
Yeah, I think that's a good way of saying it.
If the science detectives at CERN are going to find more clues as to how the universe really works, they're going to need a bigger and better magnifying glass.
In 2 years, the LHC is going to be shut down and upgraded. Will you have enough energy then?
So it will have basically the same energy. It might go slightly higher, but basically the same energy. But it will have much higher collision rate. So this will allow us to push this weakly interacting particle side, because if we're looking at things that are very rarely produced, we need more collisions to see them. And with the high luminosity LHC, which is what this upgrade's called, it will give us 10 times more collisions to search for these type of things.
So that's what you mean when you say the higher luminosity phase of the Large Hadron Collider.
Exactly, yeah.
Higher collisions, not higher energy.
Exactly.
The upgrade Jamie is talking about is scheduled to start at the end of 2025. Mirko Pollier is one of the scientists responsible for that upgrade, and he took us to show what kind of changes they're going to make.
Oh, here we go.
Yes,
This is a trick.
of course it is a trick.
Because we can't get down into the real tunnel, can we?
The LHC uses liquid helium to maintain its machinery at supercool temperatures to keep it running. The helium was still being emptied out when we visited, which is why we couldn't actually go down to the real tunnel.
So that's quite convincing, actually.
Yes, it is indeed.
I felt like I was going down. So where are we now?
So we are in a copy of the real machine, reproducing magnets, the cryogenic line behind there, all the electric cables and all the installations.
So this is exactly the same materials as the real thing?
Yes, what you see there, all those cables stuck around, around the beam pipe,
Right.
this is the real magnetic part.
Right.
This is the cable, which is made of niobium titanium,
Right.
which is a superconductor, which can transport a lot of current because it has no resistance when it is cooled down at 1.9 Kelvin, which is another record of the LHC, the coolest point in the universe. So a lot of current, which produces a vertical magnetic field, which is huge. It's 8.3 Tesla, which is 160,000 times the Earth's magnetic field.
There are thousands of these magnets in the LHC, bending and tightening the particle's trajectory as they speed around the 27 kilometres of the collider. They also align the beams and keep them stable.
Every one of these magnets is like a Formula One in terms of complexity and technology. So imagine you have almost 2,000 Formula Ones in the LHC tunnel, all operating together, all have to be operating really precisely as a Formula One car
at top level.
At top level to keep the particles circulating and getting every day billions, trillions of collisions inside the LHC.
But Mirko and the scientists here want to generate 5 times more collisions at the CMS and its sister experiment ATLAS in the next phase of the LHC, which is scheduled for 2029. And that means installing even more powerful magnets.
The magnets of the LHC are presently built with niobium titanium, which is a power superconductor, but the niobium-free tin, which we are going to use, that we are already using in the magnet that will go in the tunnel in the future, are even more powerful, so they can generate even higher magnetic fields.
They're not stopping there. CERN wants to go even bigger. The future circular collider could be up to 100 kilometres long. It's not clear how much it will cost yet. Early estimates suggest at least $17 billion, but they say it's necessary to push the boundaries of science even further.
Our goal is to address open questions. And then, of course, theories develop ideas on how to answer those questions, but nature may have chosen a completely different path. So our goal is to look at the open question and try to find an answer, whichever answer nature has decided to put out there.
The scientists here are on a cosmic quest to understand all of our universe. They're not entirely sure yet how they will achieve that, and even what they may find. In fact, the only thing they're really certain of is that they must keep trying.
In a sense, the last century for particle physics was an easy century. It led to many, many Nobel Prizes, and it was amazing. And now we have the standard model, and it has completed with the Higgs. But there are many questions that are left behind. So we know that there must be dark matter. We know that there must be something that explains the difference between matter and antimatter in the universe. We know that there must be something that stabilizes the Higgs, but we have no clue on what it is. We have many candidates, and we tell the experimentalists every day to look for them, and they try very hard.
Listening to you, I'm reminded of an old mentor of mine who said a good producer is one who gets up one more time than he was knocked down. It sounds like it's the same for theoretical and experimental physicists.
Absolutely,
Yeah.
absolutely. Yeah, I mean, this is a job that the numbers don't match, anything makes sense for 3 months of your life, and then suddenly everything settles in, and for 3 days you are the happiest person because you understood all this problem, but after 3 days you are back again lost completely. So I agree that yeah, it's a lot of perseverance to try to make this job right.
But how do you keep up the motivation when you're faced with all these knockbacks all the time, you know?
Yeah, that's a good question. I also ask myself in the morning what I'm doing. But is this 3 days? Is this 3 days where everything matches? You realize that your perspective of physics, of nature, or whatever, was wrong, and it has changed, and now you don't even understand what you were not understanding before.
Right.
And so it's a great feeling, and is what keeps you going.
Because one day it'll be right.
Yeah, yeah.
Every time I come here, I tell people I'm going to CERN, to the Large Hadron Collider. I'm going to look at another detector. People always say, why? Why do we need to know all that stuff? Why do we need to spend all that money? What's your answer to them?
This institution gives a huge output to the society, in the sense that this is a factory to, let's say, to collide protons, but it's also a factory to create PhD students. And these PhD students then go to the society, and then all this expertise that they gain here, they can share it with everyone else. So this is pushing the technology to the boundaries. So many developments here, then they have implications to the medical industry, to industry in general. For me, this is valuable by itself. It doesn't need to have, let's say, a practical impact in the society. The LHC is doing a similar job. It's exploring nature at the shortest distances possible in the most extreme conditions that humans have control. And we are understanding things that 50, 100 years ago were completely unimaginable. And to me, the option where humans do not build this kind of experiments is a bit depressing to me, in the sense that we need art, not because of the practical implications, but because of the joy of it.